Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a really interesting paper, ARC-NCA, towards developmental solutions to the abstraction and reasoning corpuses. This builds on the original abstraction and reasoning corpus, ARC, but with a developmental spin. What are your initial thoughts?
I'm excited about it. The original ARC was compelling, and the fact that this new corpus, ARC-NCA, is focusing on developmental solutions seems promising. It's like, okay, deep learning has hit a wall with pure abstraction. So how do we get it to learn more like a child?
I'm cautiously optimistic. I worry that developmental solutions within the deep learning paradigm still means throwing more data and bigger networks at the problem. I'm hoping they're actually exploring neuro-symbolic approaches or something that moves beyond brute force statistical learning.
Yeah, I share that concern. I'm also wondering if the emphasis is still too heavily weighted toward the reasoning aspect and not enough on how those abstractions are actually grounded in spatiotemporal reality. We don't reason in a vacuum, you know?
Right. The paper emphasizes solutions that can develop over time, that are not just one-shot answers. This is definitely a step toward more biologically plausible AI, where learning unfolds gradually.
See, that's where I get excited. The sheer volume of data we can throw at these things now is astounding. If we can design the architectures right and give them the right developmental training, I think we're on the path to AGI.
I don't know, Otto. I'm still not convinced that just scaling up deep learning is the answer. It feels like we're optimizing for pattern recognition rather than true understanding. Think about how a child learns. It's not just about memorizing correlations, it's about building a symbolic model of the world.
Exactly. And it's about interacting with the world, manipulating objects, understanding cause and effect in a very physical, spatiotemporal sense. Current deep learning seems divorced from that embodied experience.
So let's unpack that a bit. The ARC-NCA corpus, as I understand it, is designed to assess a system's ability to solve abstract reasoning problems, things that humans can easily grasp, like completing patterns, identifying analogies, that kind of thing. But what makes it different is that it encourages developmental approaches, systems that learn incrementally and adapt.
Yeah, and the thing with RC is that it's explicitly designed to break current AI. It's not about recognizing cats and images. It's about truly abstracting away from the specifics and understanding the underlying rules, which is something deep learning, for all its successes, still struggles with.
But how much of that struggle is due to the limitations of the data representation? I mean, if you're feeding these networks raw pixel data, how can you expect them to discover abstract concepts like symmetry or transformation? It's like trying to teach someone calculus before they understand arithmetic.
That's a great point. And it ties into this coordinate system translation idea I've been wrestling with. You need to be able to, in essence, translate the visual representation of a square into its symbolic representation, its mathematical description, and even its conceptual representation as a shape with 4 equal sides and 4 right angles. Deep learning is missing that translation step, I think.
So how might we incorporate that? I keep thinking about hierarchical processing in the brain, where information is gradually abstracted as it moves up the processing stream. Could we design AI architectures that mimic that, with different layers handling different levels of abstraction and translation?
I think that's what the best deep learning architectures are already trying to do, in a way. Convolutional neural networks, for example, are designed to extract features at different scales. But maybe we need to be more explicit about that translation process, like Donald's suggesting. We need to build in some kind of coordinate system translator module.
Or instead of trying to retrofit symbolic reasoning onto neural networks, why not start with a symbolic system and then use neural networks to learn the mappings between symbols and sensory data? That's the neuro-symbolic approach in a nutshell.
Yeah, and I think the key is to make that mapping process dynamic and context dependent. It's not just about having a static dictionary of symbols, it's about understanding how those symbols relate to each other in different situations, how they transform and interact in space and time.
Okay, so let's say we're building an AI to solve ARC-NCA problems. How would each of you approach it, given your perspectives? Otto, what's your deep learning solution?
Okay, so I'd start with a transformer-based architecture, something like a vision transformer, but specifically tuned for this kind of task. The key is to pre-train it on a massive dataset of similar abstract reasoning problems. I'd also experiment with different forms of attention mechanisms to see if we can get the network to focus on the relevant parts of the input. And of course, more data. Always more data.
My approach would be completely different. I'd start with a logical reasoning engine, something that can manipulate symbols and apply rules. Then, I'd use neural networks to learn to recognize objects and patterns in the input images and translate them into symbolic representations that the reasoning engine can understand. So, a hybrid system, where each component does what it's good at.
I'd be focusing on the spatiotemporal aspects of the problem. I'd want to build an AI that can track objects and their relationships over time, and that can understand how those relationships change as the problem evolves. Maybe something based on graph neural networks, but with a strong emphasis on geometric reasoning and coordinate transformations.
That's fascinating. It seems like there's a consensus that we need something beyond pure deep learning. The question is, how do we integrate these different approaches? How do we bridge the gap between neural networks, symbolic systems, and spatiotemporal reasoning?
I think the answer lies in the architecture. We need to design networks that are explicitly structured to handle different types of information and to translate between them. Maybe something with separate modules for perception, reasoning, and action, with clear pathways for information flow.
And we need to be careful about the assumptions we're making. Deep learning models often assume that the data is independent and identically distributed, but that's clearly not the case in the real world. We need to build systems that can handle non-stationarity, that can adapt to changing environments and learn from limited data.
Yeah, and we need to think about embodiment. Intelligence isn't just about solving abstract problems, it's about interacting with the world, manipulating objects, and achieving goals. We need to build AI that can understand the physical consequences of its actions.
So what are some specific research directions that emerge from this discussion? If we were to design the next iteration of the ARC-NCA, what should we focus on?
I'd want to explore different pre-training strategies. Can we pre-train a deep learning model on a massive dataset of synthetic abstract reasoning problems, and then fine-tune it on the ARC-NCA? I'd also be interested in seeing how different regularization techniques affect the generalization performance.
I'd focus on developing new neuro-symbolic architectures that can explicitly represent knowledge and rules. I'd also want to explore different ways of integrating neural networks and symbolic systems, maybe using attention mechanisms to guide the reasoning process.
I'd want to create a dataset that includes not just the abstract reasoning problems, but also the spatiotemporal context in which they occur. Maybe we could use virtual reality to create simulated environments where the AI can interact with the problems and learn from its actions. I'd also focus on developing algorithms that can translate between different coordinate systems, maybe using ideas from differential geometry or topology.
From my perspective, I'd like to see more research on biologically plausible AI architectures. How can we incorporate insights from neuroscience into the design of AI systems? Can we build AI that learns and reasons in a way that more closely resembles the human brain? I'm also very interested in exploring the potential for using neural circuit models to improve reasoning performance.
One thing I'd add is that we need better evaluation metrics. The ARC-NCA is a good start, but we need metrics that can more accurately assess the generalization abilities of AI systems, and that can distinguish between true understanding and mere pattern matching. Maybe we could use adversarial examples to test the robustness of the AI.
And we need to be more critical of the claims that are being made about AI. Just because an AI can solve a particular problem doesn't mean that it's intelligent in the same way that a human is. We need to be careful about anthropomorphizing AI and about overstating its capabilities. This will help us keep realistic expectations about these models.
Absolutely. And we need to be mindful of the ethical implications of AI. As AI becomes more powerful, it's important to ensure that it's used for good and that it doesn't exacerbate existing inequalities, especially as the role of AI is becoming more central.
Those are all excellent points. It's clear that the quest for AGI is a complex and multifaceted challenge, and that it requires a multidisciplinary approach. We need to bring together insights from neuroscience, computer science, mathematics, and philosophy to make real progress.
And a lot more data.
And a lot more critical thinking.
And a lot more attention to the spatiotemporal grounding of intelligence.
Well, this has been a fascinating discussion. It's clear that the ARC-NCA is a valuable tool for pushing the boundaries of AI research, and that it can help us move towards more developmental and biologically plausible AI systems. Thanks for joining me today on Cognitive Spirals, and until next time, keep exploring.